Welcome back to Calculus 2. In this lecture, we're going to introduce another test for determining if a certain infinite series is convergent, something called the alternating series test. So far, we've looked at infinite series where all the terms were positive for the most part. Now we're going to start looking at what are called alternating series, where the terms alternate signs back and forth between positive and negative values. All right, so just to start, what we're defining and introducing called an alternating series, the terms have to alternate back and forth forever between positive and negative. So we have an example here called the alternating harmonic series, very similar to the harmonic series that we introduced earlier. This one's going to be of particular importance for some technical things as we move on in a little bit. All right, so notice here the terms start with positive 1, and then negative 1/2, positive 1/3, negative 1/4, positive 1/5, so on and so on. All right, that's going to be what we are calling an alternating series. The terms are alternating back and forth forever. It has to be strictly back and forth. There can't be several positive terms and then a single negative. It has to be positive, negative, or vice versa, all the way through all infinite terms. All right, so we're going to introduce the general form of what we're calling an alternating series. These are usually very easy to pick out and identify from the general nth term. Most of them have what we're going to introduce here and call the alternating term, a term of the form -1 to some sort of nth power. Here, we have it as -1 to the n+1 power. Now, if you just think about what happens to that for different values of n, you're either taking an even power of -1 or an odd power. And if you take an even power of -1, that'll become +1. And if you take an odd power of -1, that'll evaluate to -1. All right, there is another version for what we're calling the alternating term. It could be just -1 to the n. And that's going to come in when we're starting our index for our infinite series, typically with 0 rather than 1 like we have here. Just make sure you're comfortable with that switching back and forth. Some textbooks and references refer to these alternating series, the general form starting with n = 0. Here, ours refers to n = 1. It essentially doesn't matter. It's just a way to label the terms. All right, now the other part of that nth term, the factor b sub n, that's going to play a role in what's called the alternating series test, which we have stated here. So there's a few conditions or criterion for the alternating series test. This is also known as Leibniz's test. This was kind of first discovered and used by Leibniz, one of the co-discoverers of calculus, like Newton. All right, and what the alternating series test says for the conditions is they are 3 conditions on the non-alternating term b sub n. All right, the first condition, in order to have a truly alternating series, one that goes back and forth between positive and negative values forever, the positive and negative signs have to only come from the alternating term, -1 to the n or -1 to the n+1. The other factor, b sub n, has to be strictly positive. That prevents any double negatives canceling to give a positive, kind of maybe screwing up the alternating nature of what we want for an alternating series. All right, that is the first condition, that the terms b sub n, the non-alternating terms, have to be strictly positive. A second condition for b sub n is that the non-alternating term b sub n has to be decreasing. So as n gets bigger, as we count up from n = 1, n = 2, n = 3 through all the terms, the term b sub n has to get smaller. And then the third condition is that the term b sub n as n goes to infinity, has to approach 0. Now, these are all simple criteria to check, and if all 3 of these are met or satisfied, then the conclusion with the alternating series test is that our alternating series in question is convergent. And this is a really nice, simple, quick test to apply when we have an alternating series. Now, one thing I want to be clear on before we get to some examples is what this theorem or test says. It only tells you if the alternating series is convergent. It doesn't say anything about if the alternating series is divergent. And just to be clear about what this theorem or test says is if all 3 of these conditions are met, then you reach the conclusion. If all 3 conditions are met, the conclusion of this theorem or test is that the alternating series is convergent. Just be careful, if any of those 3 conditions are not satisfied or fail, then we just simply can't apply the alternating series test, and we would have to try another test. All right, let's go ahead and take a look at an example, probably the standard example to apply the alternating series test to. For our first example is the alternating harmonic series. So let's make that example 1. Let's use the alternating series test to determine if the alternating series is convergent. All right, first thing we would want to do is identify our term that's non-alternating, the b sub n, referenced in the alternating series test. So if we take a look at our general term, -1 to the n plus 1 power divided by n, let's just strip off that alternating term, move it out front, and what we're left with is a factor of 1 over n. So what we can identify here, what's multiplying your alternating term? It's just 1 over n. We're going to identify that as b sub n, as referred to in the alternating series test. All right, if we check all of the conditions for the alternating series test, 1 over n is certainly positive for all values of n. 1 over n is decreasing. That, I think, is pretty easy to see. 1 over n is a fraction. N is getting bigger, the denominator, and if the denominator gets bigger, that fraction gets smaller. So 1 over n is decreasing. And 1 over n, the limit as n approaches infinity of that is 0. So what we have here is all 3 conditions for the alternating series test are met, and the conclusion we reach is that this alternating series, the alternating harmonic series, is convergent. Really quick, really nice and simple to apply, and there's some interesting follow-ups we can give referring to the alternating harmonic series. Now, this is going to play a role in some things we'll be getting to later. One of the interesting things about the alternating harmonic series is that there is a known sum for it. And if you were to add up those numbers, 1 plus -1/2 plus 1/3 plus -1/4 plus +1/5 plus -1/6, so on and so on forever, the sum of that infinite alternating harmonic series is natural log of 2. All right, another interesting thing to mention about the alternating harmonic series is the terms are very similar to those from the harmonic series. So if we recall what the harmonic series one was, this was just where the nth term was 1 over n. There was no alternating term. The terms for the harmonic series are 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, so on and so on. Now keep in mind why the harmonic series is a little counterintuitive. The nth term, or general term, 1 over n, does get smaller. And in fact, it gets smaller towards 0. However, the terms that you get, 1, a half, a third, a quarter, a fifth, while they are getting smaller, they're not getting small enough, fast enough for this sum, this infinite series, to converge. So we have here, if you recall, that the harmonic series is divergent. We most recently looked at that as a p series where the power p is 1, which falls into the divergent case of the p series. Now, if we take a look at the harmonic series, if we just change half of the signs from positive to negatives, that turns it into now a convergent infinite series, what we call the alternating harmonic series. So make a small change and we get, instead of a divergent infinite series, a convergent infinite series. All right, let's move on to a final second example, just to see how well you're doing with kind of all the different tests that we're kind of developing for infinite series and determining their convergence or divergence. All right, let me give you an attempt at example 2. And you're going to be asked, like we've been looking at, to just simply determine if the given infinite series is convergent or divergent. Pause the video and we'll check in a few minutes. Welcome back. Let's go through our final example here for this lecture. This one is kind of written in a form to tempt you into applying the alternating harmonics, alternating series test. So let's go ahead and see what we get by maybe trying to apply the alternating series test. We can identify our non-alternating term, b sub n. It's just everything else multiplying the alternating term, -1 to the n here. Notice this is the other version, since the starting index n starts with 0. So we have our b sub n as 3/2 to the nth power. Now, if you take a look at what terms that generates, start with n equals 1, you get 3/2. Then go to 9/4 when n is 2. Then when n is 3, 27/8. And notice here, the term b sub n, they're actually increasing, they're getting bigger. And what that would mean is one of the conditions for the alternating series test, the second condition about b sub n has to be decreasing, that is not met. And all that says is that not necessarily that our infinite series is divergent, that just means since one of the conditions isn't met, we can't apply that test. So what we find here is the alternating series test doesn't apply. All right, well, fortunately, we have some other tests. And what we can do here is simply rewrite our general nth term from the original version, -1 to the n times 3/2 to the nth power. We're just going to use some basic exponent rules, as we mentioned earlier. We can combine those separate nth powers, kind of reversing an exponent rule. We can bring in -1 and multiply it to 3/2 and have that whole product raised to the nth power. You're most probably used to applying the exponent rule when you have 2 factors inside an exponent or an nth power. You can take the nth power of each factor. Here we're reversing that. Now, what's the benefit of combining those 2 nth powers into a single one? Well, we now have a number raised to an nth power. And that is exactly what we look for to identify an infinite series as a geometric series. Recall the general form, it was of the form a times r to the n. And here, our ratio, the number that we're taking an nth power of, is -3/2. And if we just check, the absolute value of the ratio, -3/2, that just becomes +3/2. That's bigger than 1. And that would imply that this geometric series is divergent. So what we find here, just simply by rewriting our infinite series, the nth term, is we find our infinite alternating series here is divergent. As we continue through our course with other tests that we'll be getting to in following lectures, we might find several tests could apply, but ideally we're always looking for maybe the simplest or quickest one to apply. Here, the geometric series approach makes this example go pretty quick.